Random Access Memory, RAM, is a memory chip which provides temporary storage for programs and data in a computer system. Data is represented in computers as binary. In binary, a bit is either 1, which represents on, or 0, which represents off. A byte is 8 bits. A kilobyte is 1,000 bytes, and a megabyte 1,000,000 bytes, and so on. The capacity of RAM in a computer system varies. Personal computers have SIMMs or DIMMs, single or double inline memory modules, which can be removed and replaced, whereas mobile phones and tablets have built-in memory. Early SIMMs were only about 128 kilobytes. However, according to Moore's law, computer power doubles every 2 years, therefore memory requirements have steadily grown. An example is NASA's launch of Voyagers 1 and 2 satellites in 1977, which had 64 kilobytes of RAM. Most modern phones have thousands of times more RAM than this, which is an effect of Moore's law. It is possible to increase the size of RAM by adding more chips. This is known to improve performance. The more RAM a computer system has, the less virtual memory is required for page swapping to disk. Hence, more program instructions and data can be held in memory. This is known to improve the performance of a computer. The processor performance is dependent on how quickly it can access memory. If access to memory is slow, it becomes a bottleneck, which slows down the speed of the fetch, decode, execute cycle, lowering the performance of the processor, as it has to wait for instructions or data to be fetched from memory. So the faster the access to memory, the higher the performance for the processor. In general, we can think of the different types of memory in a computer as having the following speed and size characteristics. Cache, very fast but small. RAM, fast and medium in size. Hard disk, secondary storage, very slow but very large. In some computer systems, if you open a lot of applications at the same time, there is more application code and data than can fit into the available RAM. So the computer uses a secondary storage device like a hard disk to store the additional code and data. If the processor accesses some data which is not currently in the RAM, it swaps out the page of the RAM to the secondary storage device and pulls in the required data. The processor can do this since the secondary storage device is very large, but swapping a page takes a long time as the access speed of the secondary storage device is very slow. If you have more RAM, it can store more code and data, which means you don't need to access the secondary storage device as often. This increases the performance of the processor, as we do not hit the bottleneck of accessing the secondary storage device as often, so we don't slow down the fetch, decode, execute cycle. When a system is not running, programs are stored in secondary memory or disk. When a program is launched, it is loaded into the RAM, where the CPU retrieves and executes the code. The operating system controls the CPU by loading the program into RAM. The CPU then performs 2 basic operations, which are to read and write to memory. As the program runs, the CPU accesses each memory location using a unique address. The CPU fetches the next instruction from RAM and executes it repeatedly. The results are stored back into the memory. This process is referred to as the fetch-execute cycle, which occurs millions of times each second.